So now that we have some shapes or geometric figures in mind, we would like to begin to talk about the transformations of these geometric figures. But in order to understand transformations, we need a deep understanding of functions. And in order to understand functions, we need to understand at least the essentials of set theory. So we will begin our study of set theory with the primitive notion of a set itself. A set is a collection of objects and in geometry, those objects are usually called points, but other terms for the objects in a set include elements and members. Now, notice that this is not a true definition because it is impossible to define a set without a circular definition, and so we accept this term as an undefined term. So let capital letter X be a set, and let lowercase letter x be a point if the point x is in the set. Then we write this notation: x is in the set x, and if the point x is not in the set, then we write this notation: the point x is not in the set x. So let's look at a familiar example. This notation, a blackboard bold letter R, is the set of all real numbers. And since this is geometry, we can simply say that this is the set of all points on the real line which contains infinitely many points. The number pi is a real number, and so it is a point in this set. But the number I, which is the number whose square is equal to -1, is not a real number, and so is not a point in this set. So next, we will take an axiom from set theory. And an axiom is a statement that is accepted without proof. And this is known as the axiom of the null set. There is a unique set, or there exists a unique set, with no points. And this set is called the empty set, or the null set. It is denoted generally with this symbol, or to emphasize its emptiness, two curly braces with nothing inside the braces. Okay, so we are ready for our first true definition. Let x and y be sets. Then x is a subset of the set y if every point x in the set x is also a point in the set y. The notation that we use for subset is an elongated letter C and sometimes with a bar underneath. So this notation means that x is a subset of y, or we could say that y is a superset of x. Now, if x is a subset of y, then we say that the set x is contained in the set y, or that the set y contains the set x. So let's look at an example. It is vacuously true that the empty set is a subset of any arbitrary set x, and this is because there are no points in the empty set that must be contained in the set x. And it is trivially true that the set x is a subset of itself because a set does not lose its elements. Okay, so new definition. Again, let x and y be sets. Then the set x is equal to the set y if and only if x is a subset of y and y is the subset of x. That is, x is equal to y precisely when the two sets contain the same points. So the condition of set equality is equivalent to the condition that each set is contained in the other. So now is a good time to discuss some notation that we will use, since this notation represents phrases that are repeatedly used in mathematics. The upside down letter A is known as the universal quantifier, and this means for every. The backwards letter E is known as the existential quantifier, or yes, quantifier, and it means there exists or there is at least one. The abbreviation IFF is the abbreviation for if and only if. And this is equivalent to what we mean when we say precisely when a backwards letter epsilon, or the abbreviation ST, is the phrase such that. So new definition, let x and y be sets. The Cartesian product of x and y, which is denoted x cross y, is the set of all ordered pairs which we denote in open parentheses, or rather in parentheses, the element x, or the point x, comma, the point y. That is, the Cartesian product of x and y is the set of all pairs x and y where the first point in the pair comes from the set on the left of the cross, and the second point in the pair comes from the set on the right of the cross. So let's look at an example. Let x be the set which contains the number 0, and let y be the set which contains the numbers 1 and 2. Then the Cartesian product of x and y is a set of ordered pairs 0, 1 and 0, 2. And the Cartesian product of y with x is the set of ordered pairs 1, 0 and 2, 0. So note that in general, the Cartesian product of x with y is not the same set, or is not equal to, the Cartesian product of y with x. However, there are some cases where it is true. The Cartesian product of the empty set with the set x is the same as the Cartesian product of x with the empty set, which is empty. And this is the empty set because there are no ordered pairs that can be created when there are no elements or no points to contribute to that ordered pair. So a note on some notation regarding a Cartesian product. Since the ordered pair x, y is an element in the set, or an object in the set, it is called a point of the set. So just to be clear, each element in the ordered pair is also called a point because it is an object in a given set, and the ordered pair itself as an object in the Cartesian product is a point of that set. So moving along, let's look at a new definition. Let x and y be sets. A relation between the sets x and y is any subset, which we'll call R, of the Cartesian product of x with y, which again is a set of ordered pairs, x, y. Now, if the set x is the same as set y, that is, they are a relation between x and itself, then the relation R is called a relation on the set x. Now, if an ordered pair xy is in the relation, we say that the point x is related to the point y, and we write x is related to y. So let's look at an example. We'll take the same sets as in the previous example. X is the set containing the number 0, and y is the set containing the numbers 1 and 2. So let R be a relation between x and y, defined by x is related to y if and only if x is less than y. Then R is a subset of x cross y, and in this subset 0 is less than 1, and so that point is included, and 0 is less than 2, and so that point is included, but that is the entire set, and so the relation R is the Cartesian product of x and y. So now let R prime be a relation between x and y and x, defined by the same definition. X is related to y if and only if x is less than y. Then R prime is a subset of the Cartesian product y cross x. But in this case, the number 1 is not less than 0, and so this point is not included. And the number 2 is not less than 0, and so that point is not included. And so there are no points in the relation, and so the relation R prime is the empty set.